Good afternoon, friend. Myself, Shishangiya Jitendra from Rajkot. I have completed my BE from Government Engineering College and I am completed my ME from Atmiya Institute of Technology and Science, Rajkot. Recently, I am working as an assistant professor at Atmiya College, Kala Road, Rajkot. Today, we deal with one subject, electrical circuit, and we go for paper solution of January 2012. So go with first question. Question number 1, state Ohm's law and its limitation. It asks for 4 marks. Okay, what is Ohm's law? Is the potential difference or a voltage across an ideal conductor is proportional to the current flowing through it, and this the constant of proportionality is called the resistance R. Means Ohm's law states that current flowing through the any conductor R is directly proportional to the applied voltage V. So as mathematical form, if we write, we can denote it V is directly proportional to current. As in mathematics, if we remove the proportionality constant, we get V is equal to IR. So equation become V equal to IR, where R is known as resistance. It also written in the form of R equal to V divided by I. Now, Ohm's law gives the relation between the 3 parameters, voltage, current and resistance. So if any 2 parameter is known, then we can find out another 2 parameter. So we can easily understand Ohm's law by Ohm's triangle. In 3 quantity, voltage, current and resistance is put according to the shown in the figure. Now if I want to find out the voltage across the conductor, then equation become V equal to I into R. As simple shown in the figure, V equal to IR. In second figure, if I want to find out the current, then current is indicated by round. So it's simple, current I equal to V upon R. It is also shown in the figure, V is in numerator and R is in denominator. That's a simple, from the figure we can know that I equal to V upon R. Similarly, if we want to find out the resistance, then resistance R equal to V divided by R. So these 3 equations are between related, so we can find out any one value using the any one equation. So Ohm's triangle is very useful. Now there is 2 limitation of Ohm's law. First, this law cannot be applied to any unilateral network. A unilateral network has unilateral elements like diode, transistor, etc. Diode and transistor do not have the same voltage current relationship for both the direction of current, either direction flowing in forward or in reverse. They have not same relationship. That's why Ohm's law is not applicable. Second limitation, Ohm's law is also not applicable for the non-linear elements. Now, non-linear elements are those elements which do not give current through it. It is not exactly proportional to the applied voltage. That means the resistance value of those elements is changes for different value of voltage and current. Example of non-linear elements are thyristor, electric arc, etc. Let's understand Ohm's law by one video.
Let's have a discussion on Ohm's law. This is very basic law of electrical engineering. This law states that electric current through a conductor is directly proportional to the applied voltage across the conductor. Before going through the detailed study of this law, we will try to understand the process of current flowing through a metallic conductor. Actually, current through a conductor depends upon drift velocity of free electrons inside the conductor. In room temperature, there are some free electrons available inside any metal body. Whenever external voltage or potential difference is applied across the metal conductor, these initial free electrons due to electric field start drifting towards the positive terminal of the conductor. During this journey, free electrons collide with other atoms of the metal and create more free electrons. Due to the same electric field, these newly created free electrons also accelerate towards the positive terminal of the conductor. But they also collide with other atoms, bounce back in random manner and reaccelerate again, and in addition to that, they also create newer free electrons. This flow of electrons means transfer of negative charge from negative terminal to positive terminal of the conductor. Rate of transfer of negative charge from lower potential to higher potential is referred as electric current from higher potential end to lower potential end of the conductor. Hence, electric current in a metallic conductor solely depends upon number of free electrons available inside that conductor. Again, number of free electrons is function of applied voltage across the conductor. As we increase the voltage across the conductor, electric field strength will increase, which increases the number of free electrons. That is, for more voltage, more free electrons tend to drift towards positive potential end on the conductor. Again, more voltage means more strength of electric field, means more acceleration of the electrons towards higher potential. Hence, at a higher voltage, more free electrons with more acceleration causes more electric current. So it can be concluded, for a particular conductor, current varies with applied voltage. And for metallic conductor, this variation is linear. That means electric current through a particular conductor is directly proportional to the applied voltage across it. This is Ohm's law. Here, we should remember some basic things such as the tendency of creating free electrons for a particular metallic conductor depends upon atomic structure of the metal. For different metals, different energy levels are required to remove valence electrons of atom to create free electron. That is why tendency of creating free electrons in silver is much higher than copper, and again that of copper is higher than aluminium. Again, as cross-sectional area of the conductor increases, the free electrons get broader path to drift. If length of the conductor increases, the potential stress per unit length, that is voltage gradient, is decreased. This also causes less free electrons to be created, hence less current. Again, if the temperature of the conductor increases, there would be more intermolecular vibration in the metallic conductor, which results in more collision of free electrons. More collision means fewer electrons drift from one end to other, hence less current. Hence, at last we can say that electric current through a conductor not only depends upon the applied voltage across the conductor, it also depends upon the material of the conductor, dimension of the conductor, and also on the temperature. If all these factors are constant, then only electric current is directly proportional to applied voltage. That means V is directly proportional to I, or V equal to R into I, where R is constant of proportionality. This R is known as the resistance of the conductor. This resistance can be determined for a particular conductor from its material, dimensions, and temperature. This is what is Ohm's law. Finally, this law states the current flowing through a metallic conductor is proportional to the voltage applied across its ends, provided the temperature and all other conditions remain constant.
Okay, next question. Next question is state and explain Faraday's law of electromagnetic induction. It asks in 6 mark. So Faraday give two laws for the electromagnetic induction. Faraday's first law, it states that whenever flux linked with circuit or coil is changes, EMF is induced in it. Or in other word, when any conductor cuts the magnetic field, EMF is induced in the conductor. Faraday's second law. Now, as first law states that there is some EMF is induced into the conductor, then what is the magnitude of that EMF? So Faraday's second law clarify about that. Faraday's second law states that the magnitude of EMF induced is equal to the rate of change of flux leakage. So here we indicate one coil and one magnet. As we move the magnet towards the coil and away from the coil, the magnetic field linkage with the coil is changed and hence EMF is induced into the coil. This EMF is measured through this galvanometer. Now the magnitude of induced EMF, how much induced, it is depends on the rate of change of flux leakage. Let's see the equation. Suppose at first instant of the time t1, the flux leakage with the coil at time t1 is n phi 1 Weber, where n is a number of turn of coil, phi 1 is a flux at particular time t1. Suppose flux leakage with the coil at the time t2. Suppose when the magnet is moved towards the coil, at the second condition the flux leakage is given by n phi 2. That means there is some changes occurs in the flux leakage. So this change in flux linkage is given by n phi 2 minus n phi 1. Taking out n as a common, we get n phi 2 minus phi 1. So let this change in the flux leakage be phi equal to phi 2 minus phi 1. This change of flux, if I denoted by the phi, then I can also write down that the change in flux linkage is equal to n phi. So the rate of change of flux leakage is given by n phi upon t, because it is a rate of change, so it is divided by the time. Take derivation on the both side, we will get the rate of change of flux leakage is equal to n d phi by dt, because flux is a variable quantity, so it is differentiated with respect to time, and is we know that the rate of change of flux linkage is equal to the induced EMF in the coil, so it given by E is equal to n d phi by dt. It using Lenz's law, we can put minus sign because induced EMF always oppose of cause of it. So actual final equation is E equal to minus n d phi by dt. Now we understand Faraday's law by one video, how it actually occurs.
Let's have a discussion on Faraday's law of electromagnetic induction. This is most important and basic law of electrical technology. We can say electrical technology is mainly based on this law. Operation of most basic components of electrical system like electrical motors, generators, electrical transformers, and inductors, etc. are based on Faraday's law of electromagnetic induction. This law shows the relationship between electric circuit and magnetic field. He found that when an electrical conductor is brought under the influence of a magnetic field, and if the flux linked with the conductor due to this magnetic field is changed, an EMF is induced in the conductor. In this experiment, Faraday takes a magnet and a coil and connects a galvanometer across the coil. At starting, the magnet is at rest, so there is no deflection in the galvanometer. That is, needle of galvanometer is at center or zero position. When the magnet is moved towards the coil, the needle of galvanometer deflects in one direction. When the magnet is held stationary at that position, the needle of galvanometer returns back to zero position. Now, when the magnet is moved away from the coil, there is some deflection in the needle, but in opposite direction. Again, when the magnet becomes stationary at that point with respect to the coil, the needle of galvanometer returns back to zero position. Similarly, if the magnet is held stationary and the coil is moved away and towards the magnet, the galvanometer shows deflection in similar manner. He also found that if these movements are made faster, the deflection of needle of the galvanometer is also more. That indicates faster the change in the magnetic field, the greater will be the induced EMF or voltage in the coil. From this experiment, Faraday concluded that whenever there is relative motion between conductor and a magnetic field, the flux linkage with a coil changes, and this change in flux induces a voltage across a coil. Michael Faraday formulated two laws on the basis of above